Hi guys. Oh, now this is better. So in this video, we'll learn the basic components of electrotherapy. So electrotherapy may sound like a bit um, a hard subject to understand, but actually the difficulty of this subject is basically because there are like so many names, different names to mean like the same thing, that this usually creates a little bit of confusion among physiotherapists. So we'll try to simplify those concepts and also to give like a general understanding of the basic terminology used in electrotherapy. So let's start with the different electric currents that exist. So the most typical electrical currents that we use in physiotherapy are basically three types. Number one, we have here, this is the direct current. This is also known as continuous, because as you see here, there is a continuous flow of electrical charges, and this flow is uninterrupted. Okay, so this flow of currents, it lasts approximately 1 millisecond. Okay, then we have so the duration here in the direct current is 1 second, okay, at least. So this is a direct unidirectional flow of electrical charges, okay, during 1 second at least. Then we have the alternating current, number two, here at the bottom. So in the alternating current, this is also known as Faradic current, okay, named because the English Faraday, that is very well known in physics, okay. And by the way, the first type, direct current, can also be called galvanic current, okay. So number one can be direct, continuous, or galvanic. They are synonyms. Galvanic because of Galvani, which was who was an Italian who first described this type of current. Okay, so number one is galvanic, two is Faradic, alternating current. Okay, which is we see that this flow of charges can have this type of waves, sinusoidal waves, okay? So it goes from positive and negative, alternating the polarity, okay? And we also have the pulsed current, which is like the most used type of current in physiotherapy. The pulse current, for example, TENS, we'll learn also in this lecture. The pulsed current is like a continuous current with pauses, okay? So it has some pauses. But to be pulsed, the polarity can also be positive or negative, okay? So it doesn't matter. It's so in a way that the flow of charges is not unidirectional only, can be bidirectional, okay? So let's go through the second type which is the medium frequency alternating current, AC. So in alternating current, medium frequency usually ranges from 1000 to 10,000 hertz. And we have a couple of types of alternating current. So let's start with the first type, which is interferential current. The interferential current is a type of current that it requires two different circuits, okay? As you see here in picture A, we have blue circuit, okay, number one, and we also have the red circuit, number two here. So two circuits meaning that we are using 4 electrodes. So let's say the main rationale for the use of interferential current is that we usually apply two circuits, and the frequencies of the two circuits, they are slightly different. The blue circuit, number one, as you see here, it uses a frequency of 5,000 hertz. And circuit number two, we have a frequency of 5,100 hertz. So they are slightly different. What happens here? The generation of medium frequency alternating current is because the two circuits, we have like an interposition, okay, of the two circuits in a way that sometimes, let's take this point here that you see the peak of circuit 1 and peak of circuit 2. So when we have this peak, we have the maximum amplitude of current which is delivered to the patient, okay, in the peak. So in a way that both circuits, they sum up together, okay, and they deliver more amplitude of frequency to the patient. So this maximum amplitude is able to reach deeper tissues, deeper muscles, okay, for example. And on the other hand, if we take the least amplitude that we have here in circuits 1 and 2, so they will also have an opposing effect, okay? So this one here is the maximum amplitude, and in this here, we are taking the minimum amplitude of both circuits. So this minimum amplitude remains in the superficial tissue, in the skin, okay? The interesting thing about using interferential current is that we use, as I told you, we use 4 different electrodes. So we have 4 electrodes here, okay? And the effect of this current is mainly generated here, right in the middle of the 4 electrodes, okay? So we have in the intersection of these electrodes, we have the potential effects and generation of currents. Okay, so the interferential current delivers more total current than the pulsed waveforms, and it may also stimulate a larger area. We have a variation of interferential current, okay, which is called premodulated current. The premodulated current, as you see here, the graph is quite similar, okay, to the first one, to the previous that I showed you before. But the difference is that the premodulated current uses only one circuit, okay? So one circuit means 2 electrodes, not 4 electrodes as the interferential current. So a single circuit, okay, it produces the alternating current by sequentially increasing and decreasing the amplitudes. And this modulation of current, okay, increasing and decreasing, this is modulated inside the device, okay, the electrotherapy device. So here inside the device, we have the modulation, okay, increasing and decreasing the amplitudes before delivering to the patient. So the patient will receive this current, which was pre-modulated inside the device. What's the difference between pre-modulated current and interferential current? Apart from using only one circuit, okay, in the pre-modulated current, the difference is that taking this amplitude that we see here, I showed you before that when we use 4 different electrodes, the frequency is the alternating frequency, the alternating current is created within the patient's tissue. So we place 4 different electrodes, and then in the intersection of these 4 different electrodes, the alternating current is generated. So the intersection is within the patient, okay, not inside the device. So this is another difference comparing pre-modulated current and interferential current. We have another type of alternating current, which is called Russian current. The Russian current is a sinusoidal current that uses this frequency of 2,500 hertz. The current is interrupted, it's not continuous, okay, so this is interrupted and delivered in bursts of long duration. So when you see here a burst is like a package, okay, of current, which is delivered during this time frame, okay, 10 milliseconds, for example, and then we have a pause, okay, of another 10 milliseconds, and then another burst is given again, 10 milliseconds, okay. So the burst duration in the original Russian protocol is equal to the interburst duration. So meaning that we have like a 50% of duty cycle, okay, on-off time. The Russian protocol gained more popularity during the 70s because the Russian they observed that using this type of current in Russian athletes, they observed more muscle strengthening and also muscle power in Russian athletes. So Russian athletes, meaning that like this healthy population was benefited by the use of this type of currents. But over the years, this type of current has been developed. And more recently, we have the Aussie current, which was created by the Australians. So the Aussie current, the principles are very similar to the Russian current. It uses alternating current modulated in bursts, but the difference here is that the bursts, they have shorter duration, okay? So in the Russian protocol, we had here 10 milliseconds, and the Aussie current, we have bursts that ranges from 2 to 4 milliseconds. So these shorter duty cycles, okay, because we have like on time is 4 milliseconds and off time we have 16 milliseconds. So we have more time to rest, okay. So these short duty cycles creates a more current for the patient. So patients usually find AC current more comfortable than Russian current. The frequencies are also different from the Russian. So the AC current can use frequencies of 1 or 4 kilohertz, or 1000 or 4000 hertz, that are mainly used for neuromuscular stimulation, this one here, or analgesia, this one here, okay, 4. And the big advantage compared to the Russian is that AC current produces greater torque in the muscle and also reduces the rate of muscle fatigue in the patients. So those are like the big advantages. And the third type of current is the pulsed current. Okay, so the pulsed current can be either monophasic or biphasic. An example of monophasic current is the high-volt pulsed current, HVPC. Is mainly used for wound healing and edema resolution. We will learn in the next class. And this current here flows in only one direction during a pulse. Okay, so this is monophasic. Okay, and the biphasic means that the current flows back and forth during a pulse. So I will give you some more definitions regarding these graphics here. We have, I was talking about pulse and phase. So this is one pulse, as you see here, okay? And this is a phase, okay? So during a pulse, the current flows back and forth, okay? So one pulse and a phase is here, the total, okay? And biphasic currents are mainly used for analgesia. So TENS is the most used biphasic current for pain management. Biphasic currents, they can be symmetrical or asymmetrical. Okay, so now we are talking about different waveforms. Okay, so the first example here, we have an example of symmetrical current. Okay, symmetrical and biphasic. Here at the bottom, we see that this graph here represents a biphasic current and asymmetrical. Asymmetrical because here we have a rectangular and then a triangular shape. Okay. By the way, these shapes, they can be either a square, a rectangular shape, or a triangular shape. Okay, but this this is asymmetrical, okay, because the shape is different. If this is asymmetrical, it has also another classification. Asymmetrical currents, they can be balanced or unbalanced. So still taking this example here of a rectangular shape and a triangular shape. This is asymmetrical because the shapes are different. But the area of the square is equal to the area of the triangle. So x is equal to y. So if the areas are the same, so this current is balanced. If the areas here, x, is different from y, this current is unbalanced, okay? And so taking all these types of currents that you now have been introduced, we have to bear in mind that those currents, some of them, they can have ionic effects on the tissues, on the human body, okay? And some of them, they don't cause any ionic effect. So direct currents, for the continuous current or galvanic, for example, represented here in blue, the monophasic pulsed and the unbalanced biphasic waveforms, they produce ionic effects in the tissue, as you see here, because the flow is like unidirectional, okay? And this unidirectional flow of charges causes net charges or ionic effects to the tissue. So that's why this type of current, okay, direct current, is, for example, used for tissue healing, okay, because of the net charge that it creates. But the predominant electrical currents that we use in physiotherapy, they have balanced biphasic waveforms. Therefore, they do not leave any charge to the tissue. So, for example, we have the alternating current or the balanced biphasic current. As you see here, the green graph and the red one here, the net charge is 0 because they are balanced, okay? So those type of currents, they have like another use. So they are more used for muscle strengthening or for pain modulation. We have here this example that you all learned in the ultrasound lecture. We learned about phonophoresis, which is basically the use of gel, a medication, to be delivered through the skin by means of an ultrasound. Okay, so this is phonophoresis. And in electrotherapy, we can also use something that is similar to phonophoresis when we apply medication in gel, for example, okay? But we use electrical current to deliver this medication through the skin. And this is called iontophoresis. So iontophoresis can be used to potentiate transdermal drug penetration. We have these examples here, okay, different conditions, and the medication that is frequently used with iontophoresis. I will highlight those two medications, which are like lidocaine, which is a medication is an analgesic, and dexamethasone, which is anti-inflammatory medication. Okay, so these two examples here are different medications and they have different polarities. Okay, lidocaine has a positive polarity and dexamethasone has a negative polarity. So how does iontophoresis work? We basically have the electrotherapy machine, okay, which is coupled with electrodes. So we will place electrodes next to the area to be treated, okay? And if we want, for example, to induce analgesia to the area, Okay, we use lidocaine, which has, as you see here, a positive polarity. So in the case of lidocaine, which has a positive polarity, I will use the electrode, okay? So we have basically, in a circuit, we have two electrodes, a positive and a negative electrode. So in the case of lidocaine, I will use a positive electrode next to the area to be treated and apply the medication over the electrode, because the electrodes, they are adhesive electrodes, and we can add some gel to these electrodes. Uh, Not all of electrodes, okay? Some electrodes, they don't require gel because they stick directly to the skin. But if we want to apply iontophoresis, we can apply gel with the medication, okay? And the principle is that the positive electrode, okay, of my circuit will repel the positive charges of lidocaine. So as we all know, same charges. So if I have positive in my electrode and positive in my medication, same charges, they are repelled. Okay. So this current will repel the medication, and therefore it will potentiate the delivery to the skin. Okay, so that's why we must know the polarity of the medication and also the polarity of the electrode that we want to apply for the patient. If we use the same, if we use different polarities, for example, the lidocaine, if I use negative pole to the medication, which has a positive polarity, the medication will be attracted to the electrode. Okay, so this is the difference. If you want to potentiate the delivery to the transdermal delivery, we must think about repelling the charges, okay, not attracting the charges. So that's the thing.